February 7th, 1944. Burtonwood, England, the largest military airfield in Europe. The sound hits you first, a mechanical thunder that rattles windows in Warrington 5 miles away. Wright R-1820 Cyclone engines, 73 of them running simultaneously on test stands, each one screaming at 2,500 RPM, each one being pushed to its absolute limit by men who needed to know if it would fail here on the ground or 30,000 feet over Germany with 10 lives depending on it. Staff Sergeant Joe Rossi stood in test cell number 12, with his hands on a vibration gauge and grease already under his fingernails, watching needles dance across dials that measured oil pressure, cylinder head temperature, and magneto timing. The engine in front of him, serial number 42-7391, had come out of a B-17 called Lucky 13 that limped back from Schweinfurt 3 days earlier with its number 3 engine running so rough the pilot thought it would shake itself off the wing. Rossi had torn it down to the crankshaft, replaced 14 cylinders, 2 magnetos, rebuilt the supercharger, and spent 11 hours with a timing light and a wrench, making sure every spark plug fired at exactly the right microsecond. Now he needed to know if his work would hold, or if some crew would be fighting a dying engine over the North Sea because he missed something. The 8th Air Force in early 1944 had a problem that kept generals awake at night and made logistics officers physically ill when they updated the readiness boards. Every morning, roughly 50% of the bomber fleet sat grounded, not from battle damage, though there was plenty of that, not from parts shortages, though those were chronic, but from engines that wouldn't run right, magnetos that wouldn't stay timed, and a maintenance system that was drowning under the sheer mechanical violence of flying 4-engine bombers into combat, day after day after day. A B-17 Flying Fortress had 4 Wright Cyclone engines. Each engine displaced 1,820 cubic inches, generated 1,200 horsepower at takeoff, and contained approximately 7,000 individual parts that all had to work in perfect synchronization, or the whole thing became 3,700 pounds of useless metal. The 8th Air Force in England operated roughly 1,000 heavy bombers by February 1944. That's 4,000 engines that needed constant maintenance, regular overhauls, and immediate replacement when battle damage or mechanical failure made them unflyable. Do the math. If each engine needed a complete overhaul every 200 hours of flight time, and the average bomber was flying 3 to 4 missions per week at 8 to 10 hours per mission, you were looking at an engine lifespan of maybe 6 to 8 weeks before it needed to come off the wing and go to depot for rebuild. 4,000 engines, 8-week cycles. That meant approximately 500 engines needed complete overhaul work every single week just to keep pace with operational tempo. And that assumed nothing went wrong, which in combat operations over Nazi Germany in 1944 was an assumption that got people killed. The official solution from Washington was to build more engines, ship more replacements, and maintain larger stockpiles. Standard peacetime thinking applied to a war that ate machinery faster than factories could produce it. But at Burtonwood, 30 miles east of Liverpool in Lancashire, something else was happening. Something that would turn the 8th Air Force's engine crisis from a strategic problem into a solved equation. And it started with men like Joe Rossi, who understood that the real war wasn't just fought over Germany. It was fought every night in maintenance hangars by mechanics who refused to let their airplanes fail. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Rossi had arrived at Burtonwood in August 1943, fresh from technical school at Chanute Field, Illinois, where they'd taught him how to identify engine parts, read technical manuals, and follow procedures exactly as written. 22 years old, third-generation Italian-American from South Philadelphia, he'd been working on car engines since he was 14 in his uncle's garage. The Army Air Forces looked at his mechanical aptitude scores and sent him to engine school. 6 months of classroom instruction on theory, specifications, and proper maintenance procedures, according to technical orders written by engineers who'd never seen an engine come back from Schweinfurt with 3 cylinders blown out and metal shavings in the oil. His first week at Burtonwood, Rossi watched a civilian contractor from Wright Aeronautical, the company that built the Cyclone engines, reject an engine that had just completed a 200-hour overhaul because one cylinder was running 15 degrees hotter than specification. The book said to reject it. The contractor rejected it. The engine went back for another teardown and rebuild. 3 days of work, one engine out of rotation. Somewhere in England, a B-17 sat with an empty engine mount waiting for a power plant that met peacetime engineering standards. Rossi asked his crew chief, Master Sergeant Frank DiNardo, a question that got him either respect or trouble depending on who was listening. "Sarge, how hot do these engines run in combat?" DiNardo, a former merchant marine engineer from Brooklyn who'd been maintaining aircraft since 1941, gave him a look that suggested the question answered itself. "Kid, when you're at 28,000 feet over the Ruhr, and every flak battery in Germany is throwing 88mm shells at your formation, and your turbo supercharger is screaming, and your manifold pressure is maxed because you're trying to stay in formation while the whole airplane is getting bounced around by prop wash from 3 other B-17s, that engine is running whatever temperature keeps it running. Spec says 260 degrees cylinder head temp is maximum. Combat says 400 degrees is Tuesday." The disconnect was fundamental. Wright Aeronautical had designed the R-1820 for reliability under controlled conditions. The Army Air Forces was operating them under conditions that would make a design engineer weep. Maximum continuous power settings that were supposed to be emergency only became standard procedure in combat. Engines that were designed to run smooth at cruise power were being redlined for hours at a time. The maintenance manuals assumed careful operation. Combat assumed survival. Burtonwood existed because someone in the 8th Air Force had done the logistics math and realized that sending damaged engines back to the United States for depot-level overhaul meant a 4 to 6 month turnaround time. Ship it across the Atlantic, process it through the depot system, rebuild it, ship it back. By the time an engine returned from stateside overhaul, the war might be over, or at least the bomber that needed it would certainly be flying with a different engine or not flying at all. Base Air Depot No. 1, as Burtonwood was officially designated, became operational under American control in June 1942. By February 1944, it had grown into something unprecedented in military aviation history, over 18,000 American personnel, the largest aircraft maintenance and supply facility in Europe, and, at its core, the engine overhaul operation that would process more than 2,200 engines per month at peak production. The scale was industrial. Building 6 housed the engine disassembly line, where incoming engines from combat units were torn down to individual components. Building 8 contained the cleaning and inspection operation, where every part was measured against specification to determine if it could be reused or needed replacement. Building 12 was the rebuild assembly floor, where engines were reassembled by teams working in systematic progression, and buildings 14 through 18 housed the test cells, where rebuilt engines ran for hours under load to prove they could handle combat conditions. But scale alone didn't solve the problem. What solved the problem was the realization that peacetime specifications didn't work in wartime operations, and somebody needed to rewrite the rules before more bombers went down from preventable mechanical failures. That somebody turned out to be a collection of mechanics, crew chiefs, and civilian contractors who started asking dangerous questions about why they were rejecting engines that would probably run fine in combat while operational squadrons were cannibalizing parts from 3 broken bombers to keep one flying. Sergeant DiNardo had been a crew chief in the 401st Bomb Group before transferring to Burtonwood in January 1944. He'd watched bombers abort missions because an engine wouldn't maintain proper oil pressure according to the manual, even though the engine ran fine and the pilot could have flown the mission. He'd seen crews die because a replacement engine wasn't available, so a marginally airworthy bomber flew anyway and didn't come back. And he'd spent enough nights lying awake doing math to know that the official maintenance system was failing at a rate that was going to lose the air war unless something changed. What changed was the tolerances. Not officially. Nobody filed paperwork with headquarters asking permission to modify acceptance standards. But in the test cells at Burtonwood, Men like DiNardo started making decisions based on combat reality instead of engineering ideals. That cylinder running, 15 degrees hot? If it held steady under load and didn't show signs of detonation, it passed. Oil pressure slightly below minimum spec? If it stayed stable and the bearings weren't showing wear, it passed. Magneto timing off by 2 degrees? If both mags fired consistently and the engine ran smooth, it passed. They called it practical tolerance, and it was technically unauthorized modification of acceptance standards. But it worked, because the men making these decisions understood something the technical manual writers didn't. An engine didn't need to be perfect. It needed to be reliable enough to get a crew to the target and back home. Perfect was a peacetime luxury. Reliability was a wartime necessity. Rossi learned this not from manuals, but from watching DiNardo make calls that would have gotten him court-martialed if anyone with enough rank had been paying attention and cared more about regulations than mission success. The real innovation at Burtonwood wasn't just accepting engines that fell slightly outside peacetime specs. It was the systematic analysis of what actually failed in combat and why. Every engine that came back from a combat unit arrived with a maintenance form detailing its history. Hours flown, missions completed. Any mechanical issues noted by crew chiefs or pilots, and critically, if it had been pulled because of combat damage or mechanical failure, exactly what went wrong. DiNardo started keeping notebooks, not official logs, but personal records tracking patterns in failure modes. By March 1944, he had data on over 400 engines that had come through Burtonwood's overhaul system, and the patterns were undeniable. Magneto failures accounted for 38% of mechanical issues, not because the magnetos were poorly designed, but because the vibration and temperature extremes of combat operations were outside what Scintilla Magneto Company had tested for when they designed them. Cylinder failures, usually, cracked heads or blown gaskets, represented 23%, supercharger problems, another 18%. But here's what the data showed that the engineering manuals didn't account for. The engines that failed weren't necessarily the ones that showed the most wear. They were the ones that had been overhauled most recently. New overhauls meant new parts, tight tolerances, everything by the book. And tight tolerances meant no break-in period, no settling, no accommodation for the reality that metal expands, gaskets compress, and bearings seat themselves through operation. Engines that had 50 to 75 hours on them since overhaul failed at twice the rate of engines with 100 to 150 hours. The sweet spot was between 75 and 175 hours. After that, wear patterns started causing problems. But that middle range, where everything had settled in and was running as a system rather than a collection of new parts, those engines were bulletproof. DiNardo's solution was radical and completely unauthorized. Instead of shipping freshly overhauled engines directly to squadrons, Burtonwood started running them through extended test cell operations. Not the standard 2-hour acceptance test that the manual called for. 8 to 12 hours of progressively increasing load, cycling power settings, temperature variations, the kind of stress cycling that simulated what the engine would see in combat. They called it seasoning, and it meant that engines leaving Burtonwood had already been through their break-in period before they ever got bolted to a B-17. The failure rate on newly installed engines dropped 47% in the units that received seasoned engines compared to standard overhauls. 47%. That translated to approximately 60 fewer engine failures per month across the 8th Air Force. 60 fewer aborted missions. 60 fewer instances of bombers trying to make it home on 3 engines instead of 4. But running engines for 8 to 12 hours in test cells meant burning fuel, wearing out test cell equipment, and tying up facilities that were already running at maximum capacity. It also meant Burtonwood's official production numbers looked worse on paper because engines were spending more time in the system before being released. The bean counters in headquarters saw throughput dropping and started asking uncomfortable questions about efficiency. DiNardo's response, delivered to a lieutenant colonel from 8 Air Force Service Command who showed up to investigate the numbers, became legendary at Burtonwood. "Sir, you can count engines pushed out the door, Or you can count engines still running when crews need them over Germany. I can give you impressive production statistics, or I can give you engines that don't quit. Pick one, because I can't give you both with the resources we've got. The lieutenant colonel, whose name was Robert Hammond and who'd been a production manager at Packard Motor Car Company before the war, spent 3 days at Burtonwood reviewing Donado's data. Then he went back to headquarters and quietly made sure that Burtonwood's seasoning protocol became unofficially official policy, not written into any technical order, not announced through channels, just quietly implemented across the depot system with a memo that referenced enhanced quality control procedures and extended operational testing protocols. By April 1944, Burtonwood was processing an average of 73 engines per day through complete overhaul. That's 73 engines disassembled, inspected, rebuilt, tested, and certified ready for combat operations every single day. 2,190 engines per month, the number that would show up in historical records as proof that American industrial might could outproduce any enemy. But the real story wasn't the production numbers. It was the men who made those numbers mean something, like Corporal Anthony Benedetti, who ran the magneto timing section and could synchronize dual magnetos to within 0.5 degrees in under 12 minutes, compared to the manual's estimated 30 minutes. His secret wasn't superior tools or some innovative technique. It was understanding that the manual assumed you'd never done it before. Once you knew the rhythm, once you understood what properly timed mags sounded like when the engine fired, you didn't need to keep checking and rechecking. You could hear it. Or Private First Class James Kowalski, a farm kid from Wisconsin who'd grown up rebuilding tractor engines and could diagnose bearing problems by the sound of metal on metal during run-up. He'd failed the written technical test twice, but could tear down and rebuild a complete engine in 14 hours, compared to the manual's projected 20 hours, and every engine he touched ran smooth. The official records would show that Burtonwood employed 18,000 American personnel at peak operations. What the records didn't show was that probably 70% of them were doing jobs they'd never been formally trained for, using techniques that weren't in any manual, and making decisions based on experience that contradicted official policy. And it worked, because warfare has a way of separating what's actually important from what merely looks good in peacetime. Technical Sergeant William Morrison ran the engine assembly section in Building 12, former Detroit auto worker who'd built engines at Ford before the war. He organized his assembly teams like a production line, which wasn't revolutionary, except that the Army Air Forces officially organized depot maintenance as individual station work, where one mechanic would perform multiple operations on a single engine before moving to the next one. Morrison's line system meant each mechanic specialized in specific operations. One man did nothing but install and torque cylinder heads all day. Another specialized in crankshaft bearing installation. Another handled accessory drive installation. It was more efficient, but it also meant if one station had a problem, the whole line stopped. The manual said it would create bottlenecks. Morrison's actual production data showed it increased throughput by 38%, because specialists got really good at their specific tasks and could spot problems faster than generalists. When a visiting inspector from Wright Aeronautical pointed out that Morrison's system violated technical order specifications for depot maintenance procedures, Morrison's response was characteristically blunt. You want me to follow the manual and get 40 engines done per day, or ignore the manual and get 60 engines done per day? Because I can't do both, and headquarters says they need 60. The inspector wrote a report. Nothing came of it. Because by April 1944, the 8th Air Force was flying missions with over 1,000 bombers at a time, and those missions required engines, and Burtonwood was delivering engines at a rate that kept the bombers flying. Everything else was secondary. The mechanics working those assembly lines were pulling shifts that would horrify modern labor safety inspectors. 12 hours minimum. 16 when missions were heavy and the incoming damaged engines stacked up, 7 days a week for months at a time. The only break was when weather grounded the combat groups, and then the maintenance crews used that time to get ahead on overhauls, so they'd have reserve engines stockpiled for when operations resumed. Rossi remembered one stretch in March 1944 where his test cell team ran for 19 consecutive days without a day off. They were testing engines as fast as assembly could deliver them, because the big week raids against German aircraft production facilities had generated massive battle damage, and every bomb group in England was screaming for replacement engines. He'd lost 15 pounds during that stretch, slept maybe 4 hours a night on a cot in the corner of the test cell building, and consumed enough coffee to float a destroyer. But every engine that left his test cell had been run through the full seasoning protocol. Every one had been pushed to maximum power for sustained periods. Every one had been cycled through every temperature range it might see in combat, and every one had his initials on the acceptance form, which meant if it failed, it was on him. That knowledge kept him awake at night, but it also meant he didn't cut corners. Ever. The B-17 crews never knew Joe Rossi's name. They never met Frank DiNardo or Tony Benedetti or James Kowalski or William Morrison. They just knew that when a crew chief said the replacement engine was good, it usually was. When they pushed the throttles forward for takeoff with 1,200 horsepower per engine, dragging 65,000 pounds of bomber and bombs down a rain-soaked runway in England, those engines kept running. When they held formation at 28,000 feet for 6 hours straight with every engine running at settings, the technical manual said were for emergency use only. The engines held together. The statistical impact of Burtonwood's operation was measurable, but not obvious unless you knew where to look. The 8th Air Force's mission abort rate due to mechanical failure dropped from 14% in January 1944 to 6% by June. That's 8% of missions that were launched and completed instead of turning back. 8% of roughly 30,000 bomber sorties per month meant 2,400 more successful bombing runs. Or look at it differently. In January 1944, the average B-17 had 3.2 engines that were fully mission-capable at any given time. By June, that number was 3.8. 0.6 engines doesn't sound like much until you realize that's the difference between a bomb group launching 30 bombers or 38 bombers on a mission. Multiply that across 40 bomb groups, and Burtonwood's engine operation was putting an extra 300 bombers in the air every day. 300 bombers, 3,000 crew members, 30,000 tons of bombs per month that wouldn't have fallen on German targets if those engines hadn't been available. The strategic bombing campaign's effectiveness wasn't just about bomber production or crew training or target selection. It was about keeping the machines running, and that came down to mechanics in grease-stained coveralls, working through the night in depot facilities that smelled like hot oil and sounded like rolling thunder. February 7th, 1944. Test Cell 12. Joe Rossi watched his needles hold steady for the final hour of an 8-hour seasoning run. The engine 42-7391 was running smooth, oil pressure nominal, all cylinders within 5 degrees of each other on temperature. Magneto drops on the left mag, 30 RPM, right mag, 28 RPM, both well within acceptable range. He signaled for shutdown. The right cyclone wound down from its characteristic roar to silence, and in that silence Rossi could hear other engines still running in test cells up and down the line. The sound that never stopped at Burtonwood. The sound meant that tomorrow morning, somewhere in England, a crew chief would bolt this engine onto a B-17 that would fly to Germany and back, and the crew would never know Joe Rossi's name, or Frank DiNardo's, or any of the men who'd rebuilt what the war kept breaking. But they'd come home, and sometimes in war, that's the only measurement that matters. The innovation that started at Burtonwood didn't stay at Burtonwood. By May 1944, mechanics from combat groups who'd been temporarily assigned to the depot for training were returning to their squadrons with knowledge that the manual didn't contain. They'd seen the seasoning protocol. They'd watched DiNardo's team make tolerance decisions based on combat reality, and they started applying those lessons at the squadron level, where crew chiefs were making life-or-death calls about whether an engine was airworthy. Staff Sergeant Eugene Hartley of the 306th Bomb Group at Thurley had spent 2 weeks at Burtonwood in April learning depot-level maintenance procedures. What he actually learned was how to read an engine's condition beyond what the gauges showed. He returned to Thurley and immediately changed how his crew evaluated engines between missions. The standard procedure said to change spark plugs every 50 hours. Hartley started inspecting plugs instead of automatically replacing them. If the electrode showed normal wear and the insulator wasn't cracked or fouled, he cleaned them, re-gapped them, and put them back in. Spark plug life jumped from 50 hours to 90 hours average. That doesn't sound revolutionary until you multiply it across 4 engines with 18 plugs each, across 30 bombers in a group, across 40 groups in the 8th Air Force. Hartley's simple inspection protocol saved approximately 15,000 spark plugs per month across the entire Air Force. More importantly, it meant fewer variables changed between missions. Old plugs that were still good meant consistent engine performance. New plugs meant break-in period, potential fouling, and uncertainty. Mechanics started preferring known good used parts over new parts that hadn't been proven in combat. It was counterintuitive. It violated every assumption about maintenance, and it worked. Technical Sergeant Raymond Chen at the 351st Bomb Group at Polebrook took the lesson even further. He started maintaining detailed logs on every engine in his squadron, tracking not just hours and maintenance actions, but performance characteristics. Engine number 7 on aircraft 42-31412 ran 20 degrees hotter on the number 5 cylinder than any other engine in the squadron, but it had been that way for 200 hours and never failed. Engine number 3 on aircraft 42-3798 had slightly low oil pressure, 42 pounds instead of the specified 45, but the pressure was rock steady and had been for 3 months. Chen's logs let him distinguish between engines that were developing problems and engines that just had quirks. The manual said both should be pulled and sent to depot. Chen's experience said quirky engines that ran consistently were more reliable than freshly overhauled engines that hadn't settled in yet. His squadron's abort rate was 4.2%. The group average was 7.1%. The difference was Chen knowing his engines well enough to trust the ones that performed consistently, even if they didn't perform perfectly. This knowledge spread informally, mechanic to mechanic, crew chief to crew chief, in conversations at the mess hall or during shift changes. No official training program, no updated technical orders, just practical wisdom moving through the maintenance community like water finding its own level. By June 1944, the 8th Air Force had effectively developed a parallel maintenance doctrine that existed alongside the official manual but delivered better results. The tension between official procedure and practical reality came to a head in late May, when a team of inspectors from Wright Aeronautical arrived at several 8th Air Force bases to investigate reports that maintenance procedures were deviating from approved technical orders. They found exactly what they were looking for: engines operating outside specifications, parts being reused beyond their official service life, maintenance decisions being made based on mechanic judgment rather than checklist. Compliance. The lead inspector, a civilian engineer named Robert Caldwell, who'd been with Wright for 12 years, spent a week at Polebrook reviewing Chen's maintenance logs and interviewing crew chiefs. His preliminary report was scathing: widespread deviation from approved procedures, insufficient documentation, mechanics making engineering decisions without proper authority. His recommendation was immediate corrective action, including possible disciplinary measures for senior NCOs who'd been allowing these practices. Then, Caldwell did something that changed everything. He asked to fly a combat mission as an observer, not in the cockpit, but in the waist gun position of a B-17 called Madam X, so he could see and hear what combat operations actually did to these engines. The group commander, Colonel Harold Price, tried to talk him out of it. Civilians didn't fly combat missions. The liability was enormous, but Caldwell insisted. He needed to see what these engines experienced before he could judge whether the mechanics' deviations from procedure were reckless or necessary. May 23, 1944. Mission to Berlin. Madam X, with 4 engines maintained by Chen's crew using their unauthorized procedures, flew as part of a 700 bomber raid. 6 hours to target and back. Caldwell wore an oxygen mask and electrically heated flight suit and stood in the waist watching the engines through the windows, while German flak burst around the formation, and the whole aircraft shook from turbulence and prop wash and the concussion of bombs dropping. He watched the exhaust stacks glow orange-red during maximum power climbs. He felt the vibration through the airframe when the engines were running at combat power for sustained periods. He saw oil streaks on the cowlings and heard the roar of turbo superchargers, pushing manifold pressure to limits that his engineering textbooks said would destroy an engine in minutes. And he watched those engines, every one of them maintained outside official specifications, run for 6 hours straight without failing. Madame X came home with flak damage to the fuselage and 137 holes from shell fragments. Not one hit an engine. But Caldwell had seen enough. His revised report, filed June 1st, 1944, contained a paragraph that essentially admitted Wright Aeronautical's peacetime specifications were inadequate for combat operations. Observed engine performance under combat conditions significantly exceeds design parameters in terms of thermal stress, vibration, and sustained high-power operation. Current maintenance procedures, as specified in technical orders, are optimized for peacetime operational profiles and do not adequately account for the extreme conditions encountered in combat. Field modifications to maintenance procedures observed during this inspection appear to enhance operational reliability rather than compromise it. Recommend engineering. Review of combat operational data to revise specifications and maintenance procedures accordingly. That paragraph didn't change official policy overnight, but it gave cover to mechanics like Chen and Hartley and the hundreds of others who'd been making practical decisions that kept bombers flying. And it validated what DiNardo and his team at Burtonwood had been doing for months. The manual was a starting point, not gospel. Combat was the real test. By July 1944, Burtonwood's engine production had peaked at 78 engines per day. That's 2,340 engines per month, each one torn down, inspected, rebuilt, seasoned, and tested. Each one represents approximately 240 man-hours of skilled labor. Each one was stamped with inspection tags from mechanics, whose names would never appear in history books, but whose work kept the strategic bombing campaign functioning. The human cost of maintaining this production rate was staggering in ways that don't show up in official records. Master Sergeant Frank DiNardo, who'd started the practical tolerance and seasoning protocols, was hospitalized in August with exhaustion and what the medical report called chronic fatigue syndrome. He'd been working 18-hour days for 11 months straight. He was 32 years old and looked 50. The hospital wanted to send him stateside for recovery. DiNardo refused and was back at Burtonwood within 2 weeks, though he'd finally agreed to delegate more responsibility to his section chiefs and limit himself to 14-hour days instead of 18. His reasoning was simple. They need engines. I know how to deliver engines. Everything else is secondary. That attitude was pervasive among the Burtonwood workforce. They weren't flying combat missions. They weren't facing flak and fighters. But they knew, with absolute certainty, that their work directly affected whether bomber crews lived or died. That knowledge created a kind of focused intensity that pushed normal human limits. Corporal Sarah Mitchell, one of approximately 600 women working at Burtonwood in various technical and administrative roles, ran the engine parts inspection section. Every component from every torn-down engine crossed her desk for measurement and evaluation. Crankshafts, connecting rods, cylinder barrels, pistons, valves, each one measured against specification, with micrometers and gauges, to determine if it could be reused or needed replacement. Mitchell had been a quality control inspector at a textile mill in Manchester before the war. She understood statistical analysis and tolerance stacking. She started tracking not just whether individual parts met specification, but which combinations of parts, even if individually within tolerance, created problems when assembled together. A connecting rod at the high end of weight tolerance paired with a piston at the low end created imbalance. She developed pairing protocols that matched components by weight and dimension to minimize vibration. It was sophisticated engineering work being done by a 24-year-old woman with a secondary school education and 3 months of on-the-job training. The official engineering staff at Wright Aeronautical would have needed months of testing to develop similar protocols. Mitchell figured it out by measuring 10,000 parts and looking for patterns. Her component matching system reduced engine vibration issues by 31% in the engines she processed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The story of Burtonwood and the mechanics who kept the 8th Air Force flying isn't one story. It's thousands of small stories. Individual decisions made by tired people working impossible hours who somehow kept producing results because the alternative was unacceptable. Private First Class David Okonkwo, who'd emigrated from Nigeria to Chicago in 1938 and enlisted after Pearl Harbor, worked in the engine wash and cleaning section. It was considered the worst job in the depot. Engines came in covered in oil, carbon deposits, and the residue of combat. They had to be stripped to bare metal before inspection. The cleaning solutions were caustic. The work was brutal. Okonkwo did it for 7 months without complaint and developed a cleaning technique using steam pressure and chemical degreaser that cut cleaning time from 6 hours per engine to 4 hours. That 2-hour savings, multiplied across 78 engines per day, meant the depot could process an additional 26 engines per day through the cleaning section. 26 engines that wouldn't have been available otherwise. Sergeant Morris Goldstein ran the magneto overhaul shop. Scintilla magnetos, the dual ignition systems that generated spark for the cylinders. Complex devices with rotating contacts, coil windings, and distributor systems that had to be timed precisely. The manual said, magneto overhaul required 8 hours per unit. Goldstein organized his shop into specialized teams and got overhaul time down to 5.2 hours. But more importantly, he started analyzing why magnetos were failing. The official explanation was vibration damage from combat. That was true, but incomplete. Goldstein's analysis showed that magnetos mounted on the number 3 and number 4 engines failed at twice the rate of magnetos on engines 1 and 2. The difference was heat. The inboard engines ran hotter because of restricted airflow. Higher heat meant insulation breakdown in the magneto coils. Standard overhaul procedures didn't account for this, so rebuilt magnetos went back onto aircraft with the same insulation that had failed before. Goldstein started using higher temperature insulation wire in his rebuilds, material that was actually designed for industrial motors, but worked perfectly in aircraft magnetos. Failure rates dropped 43% on magnetos from his shop compared to standard rebuilds. He didn't have authority to make this material substitution. He just did it because the data said it would work, and crews were dying from magneto failures. When a materials inspector eventually noticed the non-standard insulation wire and questioned it, Goldstein's response was characteristically direct. You want me to use the wire that fails, or the wire that works? Show me the regulation that says I have to use materials I know will fail, and I'll start following it. Until then, I'm using what keeps engines running. No disciplinary action was taken. By September 1944, Goldstein's higher temperature insulation wire was being quietly adopted across the entire magneto overhaul system. It never became official policy. It just became what people did, because it worked. These innovations, these small improvements in process and material and technique, accumulated into something larger. The 8th Air Force's operational statistics for the second half of 1944 showed dramatic improvement in aircraft availability. In January, average daily mission-capable rate was 52%. By December, it was 78%. That 26% improvement meant approximately 260 more bombers available for missions every day. 260 bombers, 2,600 crew members. The difference between a 1,000-plane raid and a 1,300-plane raid. The difference between hitting 10 targets and hitting 13. The mathematical impact of Burtonwood's operation rippled through every mission the 8th Air Force flew in the final year of the war. But statistics don't capture the human reality. Somewhere in that data is Second Lieutenant James Morrison, pilot of a B-17 called Duchess of Bourbon, who brought his crew home from Merseburg on 3 engines after number 4, through a connecting rod. The other 3 engines, all overhauled at Burtonwood in August 1944, ran for 4 hours at maximum continuous power to compensate for the failed engine. They held together because Joe Rossi had seasoned them properly, and Sarah Mitchell had matched their components carefully, and Morris Goldstein had installed magnetos with insulation that wouldn't fail. Morrison never knew their names. He just knew that when he needed his remaining engines to keep running, they did, and his crew made it home. That's how the connection worked. Mechanics in Lancashire kept engines running so pilots over Germany could bring crews back alive. The chain of decisions ran from depot to squadron to combat and back, and every link mattered. The war in Europe ended May 8, 1945. VE Day. Victory in Europe. The 8th Air Force stood down from combat operations. At Burtonwood, the engine overhaul line kept running. There were still bombers that needed maintenance. Still engines that needed rebuilding. The war was over, but the machinery of war doesn't stop on a schedule. It winds down gradually, like an engine cooling after shutdown. Joe Rossi mustered out in November 1945 and went home to Philadelphia. He took a job at a garage and spent the next 30 years rebuilding automobile engines. Never talked much about the war. His children knew he'd been stationed in England, knew he'd worked on bombers, but they didn't know the specifics. Didn't know their father had personally tested over 2,300 engines. Didn't know that some of those engines had been in the bombers that flew on D-Day, or the missions to Berlin, or the final strikes against German oil production. Frank DiNardo stayed in the Air Force after the war, made Chief Master Sergeant, and retired in 1963. His practical tolerance protocols and seasoning procedures eventually became semi-official, incorporated into Air Force technical. Orders in the 1950s under different names by different people who probably never knew they were codifying techniques DiNardo had developed under fire in wartime England. Sarah Mitchell married an American serviceman and moved to Ohio. Raised 4 children, worked as a quality control manager at an appliance factory, and died in 2007 at age 87. Her obituary mentioned she'd served at Burtonwood during the war, but didn't mention the component matching system that had reduced vibration failures in hundreds of engines. The official history of the 8th Air Force, written after the war, devoted 300 pages to combat operations, target selection, strategic effectiveness, and crew experiences. Burtonwood received half a page. The engine overhaul operation that made those combat operations possible was mentioned in one sentence. Base Air Depot No. 1 at Burtonwood provided essential maintenance and supply support for theatre operations. That sentence represented 23,000 man-years of labour. It represented innovation under pressure, practical wisdom overcoming theoretical doctrine, and the unglamorous reality that wars are won as much in maintenance depots as in combat. The mechanics who rebuilt those engines knew this. The crews who flew with those engines knew this. But history tends to remember the dramatic over the essential, the visible over the foundational. In 1968, the Air Force Historical Research Agency conducted a study on logistics in World War II. A researcher named Captain Elizabeth Wardwell spent 6 months reviewing depot maintenance records, trying to quantify the impact of facilities like Burtonwood on operational effectiveness. Her report contained a statistical analysis that finally put numbers to what everyone who'd been there already knew. The correlation between depot engine overhaul capacity and bomber sortie rate was nearly perfect. A 1% increase in depot output corresponded to a 1.2% increase in bomber availability. Burtonwood's engine operation, at its peak, was responsible for approximately 32% of all heavy bomber engine overhauls in the European theatre. That 32% of engines translated to roughly 35% of operational missions flown, because the engines from Burtonwood had lower failure rates than engines overhauled elsewhere. Why the lower failure rates? Wardwell's report cited 3 factors. the seasoning protocol that broke engines in before installation, the practical tolerance approach that accepted combat-proven quirky engines over theoretically perfect new ones, and the accumulated expertise of mechanics who'd processed thousands of engines and developed an intuitive understanding of what worked and what didn't. In other words, the lower failure rates came from people like Rossi and DiNardo and Mitchell and Goldstein, making decisions that violated procedure but saved lives. From mechanics who cared more about mission success than regulatory compliance. From a maintenance culture that prioritized results over process. This kind of practical wisdom is difficult to transfer through official channels. You can't write a technical order that says, use judgment based on experience. You can't train someone to have intuition. The knowledge that made Burtonwood effective was embodied in the people who worked there, and when they mustered out and went home, much of that knowledge went with them. But some of it survived. The mechanics who'd learned at Burtonwood and returned to squadron maintenance brought those lessons with them. The officers who'd seen the practical tolerance approach work became senior leaders in the post-war Air Force and influenced maintenance doctrine. The civilian contractors from Wright and other manufacturers who'd observed depot operations incorporated those insights into improved designs. The Wright R-1820 Cyclone engine that powered B-17s through World War II went out of production in 1945, but its descendants, the evolved radial engines that powered aircraft through the 1950s, incorporated design changes that directly addressed the problems mechanics had worked around during the war. Improved magneto-insulation, better component balance, more robust bearing systems. These weren't revolutionary innovations. They were engineering responses to the practical knowledge mechanics had developed by maintaining engines in combat conditions. The B-17 itself, the flying fortress that had depended on those Wright Cyclones, disappeared from frontline service by 1950. Some flew on in transport and rescue roles for another decade. A few survived to become museum pieces and airshow attractions. But the vast majority were scrapped, melted down, recycled into the peacetime economy that no longer needed flying fortresses. Burtonwood remained active as a United States Air Force facility through the Cold War, supporting various aircraft and missions. But the massive engine overhaul operation, the industrial-scale depot maintenance that had processed over 56,000 engines between 1942 and 1945, was gone. The buildings were repurposed, the test cells went silent, the accumulated expertise dispersed. The site finally closed in 1993. The runways were torn up, the buildings were demolished. Today, the location is marked by industrial parks and a theme park and a small heritage centre that preserves some photographs and equipment and the memories of people who worked there. Visitors can see a display about the engine overhaul operation. There's a Wright Cyclone engine on a stand, sectioned to show internal components. An informational placard explains how Burtonwood processed engines for the 8th Air Force. The placard doesn't mention Joe Rossi or Frank DiNardo or Sarah Mitchell or any of the thousands of mechanics who made it work. Their names aren't recorded, their specific contributions aren't documented. They were line mechanics, enlisted personnel, civilians doing war work. History doesn't typically preserve their individual stories. But their work persists in a different way. Every modern military maintenance system that emphasizes practical experience alongside technical procedure owes something to what they pioneered. Every depot that runs engines through extended testing before installation is using a protocol they developed. Every mechanic who's learned to distinguish between failing equipment and quirky but reliable equipment is applying intuition they helped establish. The official lesson from Burtonwood is about production capacity and logistics planning. The real lesson is about trusting the people closest to the problem to find solutions that work, even if those solutions violate official doctrine. About recognizing that expertise comes from experience, not just training. Understanding that in extreme conditions, the theoretical gives way to the practical, and the people who can bridge that gap are invaluable. February 7th, 1944. 73 engines running simultaneously in test cells at Burtonwood. the sound of industrial-scale warfare, the mechanical thunder that meant tomorrow's missions would launch because tonight's maintenance got done. 80 years later, that sound is silent. The engines are museum pieces, the mechanics are gone, but the principle remains. Wars are fought by the people in front, but they're won by the people behind the lines who keep the machinery running. The logistics specialists and depot workers and maintenance crews who do the unglamorous work that makes the dramatic work possible. History remembers the mighty 8th, the bombers over Germany, the raids on Berlin, the strategic campaign that helped break Nazi war production. That history is true and important, but it's incomplete, without the other story. The one about mechanics in Lancashire who rebuilt engines faster than combat could destroy them. Who innovated under pressure and made decisions that saved lives. Who understood that perfect was the enemy of good enough, and good enough kept bombers flying. Joe Rossi's initials on an acceptance form meant an engine that would run when crews needed it to run. That's not dramatic, it's just essential. And in the end, the essential is what matters. The essential is what wins. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.